6th hour, and there's a whole lot of talking. No, there's not.
Some of those
Probably. Okay, so we know how to find the sine of 60 without a calculator. But what if I asked you to find the sine of 75 degrees without a calculator? You'd probably just cry, right? Here's the idea, sum and difference. Could you think about that you could write 75 degrees as the sum or difference of two angles that we know? Would sine of 75 degrees be like the same as sine of 30 degrees plus 45 degrees? Yeah? So then the question is, what do I do with that? Well, there's a formula. If you have the sine of something plus something, you think you could just take the sine of both of them, add them together, but it's not that simple. The formula is this. No, these are just formula right now. There might be a proof later, but I'm telling you, these proofs are easier than the proofs we just did. Proofs can come up at any point now. Anytime I give you trig, I could give you a proof. So it looks kind of scary, but it's really not. If you want to take the sine of two angles added together, you're going to take the sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle. And what do you think you're going to do if you are subtracting two angles? Well, if it's the sine of subtracting two angles, you just do the same thing, except for you just subtract it. So if you don't want to write this again, you could be real fancy and you could just say plus or minus, but you don't have to. You can just write it again. And these aren't hard problems to do. The hard part is I want you to memorize these. So when you do your homework today, my goal or my hope is that maybe you don't just have these right in front of you, that you try to think about them and then you go back and look so that maybe you'll have them memorized. Because there's also a cosine one. What if you want to take the sum, the cosine of the sum of two angles? Well, it's a different formula. Couple things to notice, yes. These are just for sine. If you take the sine of two angles added together or the sine of two angles subtracted, this is what you do. But if you take the cosine of adding two angles together, then this is what you do. And so notice the differences here. For cosine, you take the cosine of the first times the cosine of the second. Something else to notice is with cosine, the sign's different in the middle. When you add, you actually subtract these two. So you take minus the sine of the first times the sine of the second. So what do you think is going to happen if I change that to u minus v? Yeah, this is the opposite sign. So again, you could write it the same, or in second hour they decided this would be too confusing, but you could say plus minus equals minus plus, but they said they wouldn't know what that means on their notes, but I think it's pretty much implied. But you can just write it a second time if you want. Good news is there's only formulas here for sine, cosine, tangent, so there's only 3 sets of formulas here, not 6. No secant, cosecant, and cotangent, if you're looking on the bright side here. No bright side. That's the silver lining. It's just sine, cosine, tangent. And sine and cosine, those are the ones that people get mixed up, so you want to make sure that you learn them. Tangent, you can't really mix up with anything, because it's its own little craziness.
Would it be really cool if you gave us like multiple choice at the beginning? That would be like, what equation does this go with? Like zero for this.
You're going to see, when we do some problems, you're going to see some problems, you're going to be like, oh, these aren't bad problems. If you just learn them, they're not that bad. And today will be easy because you have them right in front of you. If you're adding the two angles on tangent, the top's going to be plus, the bottom's going to be minus. So notice it's the tangent of the first plus the tangent of the second over 1 minus the tangent of the first times the tangent of the second. If you change this to a minus, both of these signs are going to change. The top sign is always the same sign as the problem. The denominator is always the opposite. And you're going to see as I do these today, I have no notes. I'm going to just do these from my memory. So it's possible to memorize them. But I don't really remember them until every year when I do it again. It's like the unit circle. I hate the unit circle in August, but then by the time I teach it to you again, I can do the unit circle because I just relearn it. I make you memorize a lot. It's good for your brains. Chapter 9. Pascal's triangle. No, I didn't make you memorize those. I gave those to you. I'm sure.
Honestly, can you think of a life situation I'm going to use it?
Nope.
It sounds awful to say, like, but I forget. Unless, like,
Nope. Unless you take calculus. Most of what we do in pre-calculus is for taking calculus. And in calculus, you do use that at some point if you keep going in math. But is everything you do in calculus do you use it every day? No. But 95% of what you learn in high school, there's not really real life situations that you use it in. But we use them because the state says we need to learn them, and there's standards that the state says I have to teach, and I get graded on that, and my job depends on that.
Okay.
And
Only class that has taught me life stuff is careers with
There you go.
balance sheet check.
there you go. That's about it.
it took a freshman year. I don't even have that anymore. Like, I learned how to do my taxes in econ.
There you go. That's a good life skill.
Yeah, but those are the only things
It's good. It's good for you. You don't have to take this class. There's nothing that says that you have to take this class to go to college or that you have to take this class to graduate high school, but you do it for academic honors. So that's why you have to do it, is because you're trying to get academic honors, and if you don't want academic honors, then you don't have to be in this class. Just saying. No, you won't, but it's good for your brain. Sometimes the coolest thing about math is that there's a whole lot of your brain that you don't use, and sometimes in math we force you to use it, and keeps you from getting Alzheimer's. Just so you know, the more you use your brain, the less likely you are to get Alzheimer's. So someday when you're old and you don't have Alzheimer's, you can thank me in this pre-calculus class.
I'd rather have all.
That is terrible to say, just so you know. Okay, so those formulas look bad, but I'm telling you, this is not as bad as what the stuff that we did before spring break with all those proofs where you don't know where to start. Because all you have to do on this is rewrite cosine using two angles that you know from your unit circle, and then you just plug it into the formula. It's just a formula. It's like Pythagorean theorem, just a different formula. So I'm going to pick my two angles, and I'm going to say that this is the same as saying cosine of 30 degrees plus 45 degrees. What if you said 45 degrees plus 30 degrees? Guess what? We'll get the same answer. What if you picked two other angles and subtracted them that are bigger in the unit circle? That would work too, but I usually try to stick to the first quadrant if I can, because 30 plus 45 equals 75. And then I'm just going to do that formula, which you have written right in front of you today. So today's not the hard part. The test is the hard part. And who knows, by the test, I can just be beaten down enough that I just give in and let you have the formula. So cosine, you take the cosine of the first times the cosine of the second. So you take cosine of 30 degrees times cosine of 45 degrees. And for cosine, it's always the opposite sign as the one that's in it. So since that's plus, that's minus. And then I take the sine of 30 degrees times the sine of 45 degrees. If you know that formula, all you got to do now is, oh my gosh, I expect you to still know your unit circle and tell me those values and simplify it. And the great thing is 30 and 45 and 60 degrees shouldn't be that bad to do. But 30 degrees is right here, and the ordered pair is square root of 3 over 2, 1/2. So I can say that the cosine of 30 degrees is the square root of 3 over 2. And hopefully you know that the cosine of 45 degrees is square root of 2 over 2. The sine of 30 degrees is 1/2 times square root of 2 over 2. You have to know those values. It's what we've been working on since January when we came back to school, is learning those values. So you got to know those. From here, it's just simplifying, and you're going to see that your answers are going to be very similar to each other on your homework, because you're going to get a lot of square root of 3 over 2, square root of 2 over 2 is 1/2. So they're going to be very similar answers, just maybe moved around a little bit. But when you multiply fractions, you multiply straight across the top, straight across the bottom. you are allowed to multiply radicals. So radical 3 times radical 2 is radical 6 over 4. Can I divide both of those by 2 and make that radical 3 over 2? No, because one's a radical and one's not a radical. And then this one is just radical 2 over 4. And really, there's nothing that says you can't leave your answer like this. But since they both already have a common denominator, I just can't help myself but to write that as radical 6 minus radical 2 over 4. If you left it like this, that's okay too. Can you subtract radical 6 minus radical 2 and make that radical 4? No, they're radicals. You can't add and subtract radicals, but you can multiply them. And if you really want to check your answer and it's not odd, you could take the cosine of 75 degrees on your calculator, type this in your calculator, and they should be the exact same decimal. So this is the exact answer to what the cosine of 75 degrees is.
If we ever want to approximate.
No, because you could just use your calculator to approximate it, right? Like that defeats the purpose of it. That's how I know when you take the test, if you give me a decimal answer, that you have no clue what you're doing. Because you just type it in your calculator.
I'm plugging a bunch of cosines of 0 degrees. Will these say it? Will it still be the same?
What do you mean?
I put a cosine of 0 degrees equals 0 degrees, and I kept on going out of actual 1. And then I finally put like 3 degrees or 45 degrees. Cosine of 0 equals 1, right?
Right,
So if I put it like in that the first,
right.
a bunch of zeros, would it change?
Put zeros in here,
No, you're right.
here.
Yes.
I don't understand.
We're hurting her brain for once.
I don't,
I mean, it'd still be 75 degrees, but there'd be a bunch of,
like you're going to say 0 plus 30 plus 45?
yeah,
Well, why would you do that?
because I'm a robot.
Well, here's the problem. We don't have a formula for how we do this with 3 things. You see what I'm saying? We only have a formula to how to do it with 2 things, and I don't think we can just throw in a 3rd one. You see what I'm saying?
They should figure it out. That should be their life goal.
That could be your life goal, is prove how to do it with 3.
No.
What about this? Sine of pi 12. People kind of freak out when there's fractions because we hate fractions. If you hate fractions completely, what could you do with this so that you wouldn't have to deal with pi 12s? Yeah, we could change this to degrees, right? But I'm going to show you how to do it with fractions because I want to show you that fractions aren't the worst thing. But on your homework, you can change it to degrees. I think it's 15 degrees.
If it's on the test.
I don't care. I'm just showing you. Here's the great thing. We really only have 3 angles, really, that we're dealing with if we're talking about quadrant 1. We have pi fourths, pi thirds, and pi sixths. Would all 3 of those go to 12ths pretty easily?
Yeah.
So if they give you this, I always just think about, well, what if I change this to 12ths? Wouldn't that be 3 pi 12ths? And if I change this to 12ths, that would be times 4, so that would be 4 pi 12ths. And if I change this to 12ths, that would be 2 pi 12ths. Could you figure out how we could add or subtract any 2 of those to make 1 pi 12ths? There's a couple ways you could do it. You could take 4 pi 12ths minus 3 pi 12ths, right? You could take 3 pi 12ths minus 2 pi 12ths. Both of them work. You could go other ways if you want. But I just want to show you, I'm going to do it with radians just because I want to. But if you want to do, I believe it's 15 degrees, and you could say in your head, oh, 45 minus 30 is 15 degrees. Right? That works. But I'm going to use these, and I'm going to actually write it with the regular one. So I'm going to do 4 pi 12ths minus 3 pi 12ths. So I'm going to do pi thirds minus pi fourths. And think about that. That's 60 degrees minus 45 degrees is 15 degrees. By all means, change the degrees. Because your answer is not going to have degrees in it, so that's why I don't care if you change the degrees. Like, your answer is going to look something like this. And once you do this, again, it's just using the formula. And sine's formula is you take the sine of the first times the cosine of the second. So I'm going to say that this is the sine of pi thirds times the cosine of pi fourths. Order does matter on this one because you're subtracting. Minus, because in sine it's the same as the middle. And now we switch. Now we're going to take the cosine of pi thirds times the sine of pi fourths. And yet again, that's the hardest part of the problem, because plugging in these values should not be hard. Like, you should be able to do your unit circle values. And again, you're going to get lots of square root of 3's over 2, square root of 2 over 2 1/2. It's just making sure you put the right one in the right spot. Now I'm at pi thirds. Pi thirds is up here, so it's switched around. That's 1/2 square root of 3 over 2. The sine is square root of 3 over 2. Cosine is still square root of 2 over 2. Minus cosine of pi thirds is 1/2 times sine of pi fourths is square root of 2 over 2. I think we get the exact same answer. All of them are not the same answer. I just threw this one in here just to show you. Just to remind you of one more useless math fact that you never need to know. What if you add 75 degrees and 15 degrees? What do you get? 90 degrees. What do we know about sine and cosine of any two functions that add up to 90 degrees? They're always going to be equal. We say co-functions of complementary angles are congruent. Any two angles that add up to 90 degrees, their sine or cosine will always be the same. So in second hour, they said, does that mean if I solve the sine of 15 degrees, I could just say it equals the cosine of 75 degrees? Yes. I still kind of want you to work it out. They're not going to all be like this. Okay? Switch them around. Loopholes. As long as they're correct loopholes. I'm okay with it. This is the worst part of the homework, and it's not even that bad. It's just using it. The other part of the homework is going backwards, which is super great if I gave it to you on a test, because if you forgot the formula and you saw this, hopefully it would jar your memory of what formula you need to know. But this says, write the sine, cosine, or tangent of one function, which means they're giving you the formula, and they want you to go backwards and write it as what function of what two angles are added and or subtracted together. Some crazy fractions I wrote there. And I feel like these problems on the homework are the ones that help you learn the formula the most, because you're looking at it and you have to think about which formula is it, am I adding or am I subtracting, and kind of working backwards. So which one is it? Cosine, cosine, sine, sine. Is that going to be cosine or sine as the original function? Cosine. Is it a trick to know which two functions or what two angles I'm using? It's pi sevenths and pi fifths, right? So if you know it's cosine, you know it's pi sevenths and pi fifths. The only other thing to figure out is, are you adding or are you subtracting? And in cosine, if you look at your formulas, cosine is always the opposite here of what it was in the beginning. So since this is minus, this is plus. And then you can add that on your calculator. You can just take 1/7 plus 1/5 and then put the pi with it. Just so you know, that would be a common denominator of 35. So that would be 5 pi 35ths plus 7 pi 35ths, which I think would give you a cosine of 12 pi over 35. I don't want the answer to that, because it's not going to be pretty. I just want you to put it back as one function. You get what they're asking on that? The function, like, look back at your formula. Cosine of u plus v is equal to cosine of u times cosine of v minus sine of u sine of v. So this whole thing together is equal to this. You see what I'm saying? So, like, write as sine, cosine, or tangent. Like, you should only have one function at the end. Like I said, tangent kind of looks the scariest, but honestly, it's the easiest one to recognize, because sine and cosine get mixed up because they both have sines and cosines in them. But when you see this ugly thing with tangent in it, you know it's going to be tangent. It's just making sure you know what the two angles are, which I feel like are pretty obvious, and then making sure the sine's right, which is what people get mixed up. So this one says tangent of 2x plus tangent of x over 1 minus tangent of 2x tangent of x. So I'll do the tangent part. What are my two angles? 2x and x. sign do you use? Whatever the sign is on the top. If the sign on the top is positive, you use positive. If the sign on the top is negative, you use negative. And really, someone in second hour said, do we really even have to show that step? Like, if we just know it's tangent of 3x? No, you don't have to show it, but I just like to show you where it comes from. Just kind of working your way backwards. Three more. What else can we do besides this? What if they actually ask you to find a value? So notice the directions. This one they say write as sine, cosine, or tangent, not evaluate it. But then look at these directions. Find the exact value, which means they don't want you using a calculator. They want you using the identities. So when I first look at this one, I noticed right away that it's 25 degrees and 110 degrees. Can I take the tangent of 25 degrees or 110 degrees without having a calculator? No. So that means I think that's already set up in the tangent formula. What if I work backwards? Can I go backwards and say what two angles would that be? Or like what would the angle be to go back and write it as one tangent? Yeah, just like the one we just did, it's a plus on the top, so I'm just going to take 25 plus 110. Everybody with me on where I'm getting my tangent of 135? And then in second hour, someone then said, well, let's break that up as 90 degrees plus 45 degrees, and then we can work it out, which works. But I said, isn't this already in my unit circle? I'm kind of so much in terms of radians that sometimes I forget that 135 is. But if this is the same as 90 plus 45 degrees, where is that on my unit circle? 90 plus 45. Is that right there? 135 degrees, it's already on the unit circle. If you didn't notice that and you worked out tangent of 90 degrees plus tangent of 45 degrees, it's going to work out. But you're just doing way more work than you need to, right? This is already on my unit circle. This is negative square root of 2 over 2, comma, square root of 2 over 2. What's the tangent of that going to be? It's not going to all be so pretty, but that one worked out really nice. So just make sure you look at that angle that's left. If it's already an angle that you know, you don't have to break it back up. I mean, you can always break it back up, but there's no need to. You can work it out. Just like tangent of 60 degrees. Technically, you could break that up as tangent of 30 plus 30, but why would you do that when you already know that tangent of 60 degrees? The last few questions on your homework are some proofs using this, and people are, we're kind of all scared of proofs right now because we hate them. But I like these proofs better because if they give me something with addition or subtraction in it, I know I'm supposed to use this identity. So let me show you one, and you're going to see that it's not so bad. These are nice proofs. It says prove the identity that the cosine of x minus pi halves equals sine of x. Sometimes the proofs that I give you, kind of like the ones from the quiz from last week, it's not obvious where to start. Like maybe there'll be something of get a common denominator or maybe do this. But it's not always obvious what to do. When I see something with addition or subtraction in it, I know I better break that up using the identity. So again, if you know the identity, this becomes pretty easy to do because I can say the cosine of subtracting two things is the cosine of the first times the cosine of the second. That's minus, so that's going to become plus the sine of the first times the sine of the second. And that is just the identity. That would be the part you have to know. And if you know that, all you got to do now is evaluate it. And again, remember this is a proof, and it's always better to show a little more work than a little less work. Because some people would want to just say the next step is sine x equals sine x. But show me one more step. Just go through and evaluate these for me and give me number values here. And what is the cosine of pi halves? Cosine is x. What is x up here? 0 plus, what is the sine of pi halves? And you could show more steps than this, because you could go through and say then 0 plus sine x equals sine x. But if you just show me that one extra step, I feel like that's making it easy to follow, because now this is just 0, and sine x times 1 is just sine x, and that's proof. So I like these proofs because I know when I see plus or minus, I know I have to break it up using the identity. So I have one more of these, very similar to this. I want you to try, and then I'll give you homework. No, no, not on these. There's one on your homework tonight that's like a little trickier in that they want you to break it up yourself into two things, and I'm sure we'll look at it tomorrow. But for the most part, it's just going to be something like this. Sam.
Cosine of x, cosine of pi halves, cosine of x.
Because the cosine of pi halves is 0, right? What is the x value at pi halves? It's 0. So I just evaluated it. Cosine of pi halves is 0. Sine of pi halves is 1. Like with just like knowing that up there at pi halves, x is 0, y is 1. Okay? So this one's very similar. Now show me that the cosine of x plus pi halves equals negative sine of x. And it's pretty much the same proof except for the minus sign thing. Right, again, the big step is knowing that first step for the formula. And again, cosine of pi halves is 0. Sine of pi halves is 1. So just like the last one, this cancels out, and you're just left with negative sine of x equals negative sine of x. Are they all that simple? No. I think 52 is the one on your homework that I think probably is the hardest one. I'm sure we'll get tomorrow. But try them. Look at the proofs and you know, make an attempt at them and see what you can get, especially knowing the idea that sum and difference is what you want to have happen. We're only spending 1 day on this section, which hasn't happened in who knows how long that we only spent 1 day on a section. But that's all that is in the section is sum and difference identities. So this is your homework. This is 5-3 homework. The only day. 3 through 30 multiples of 3. I think the first 3 are like our first problems where you have to come up with the 2 angles and add or subtract them and work them out. Probably lots of square root of 6s and square root of 2s in there. And then after that, it's where you have to work backwards, which doesn't really take that much work to do. And then there's 3 or 4 proofs in there, and then probably a couple of multiple choice at the end. Probably definitely going to have 1 or 2 homework quizzes this week just because I want to get some more grades in. We'll have a test next week, which will be our first test in the 9 weeks, so that will change grades a little bit. But yeah, we just have 5-4, 5-5, and 5-6 are the